There we go. Okay, hello everyone. Good morning, good afternoon, wherever you guys are from. My name is Ethan Landry. I'm part of the CGSYP committee taking over for Sarah and Nabil today. So just before we get going, at the very end, we'll do a little Q&A session. If you guys want to just post your questions in the little Q&A tab at the very top, we'll pick over the questions through that little tab there. And so today we have presenting for us is Mark Wayne. So Mark Wayne is an experienced geotechnical and geosynthetic engineer with over 30 years of experience serving as Director of Application Technology and Engineering at TENSAR International, holding engineering licenses in 7 states, authoring more than 100 technical papers, and actively contributing to AASHTO, ASTM, ISO, ASCE, and DFI in the areas of standards and development. With that, I'll pass it over to you, Mark.
Great. Thanks so much for the intro, Ethan. And thanks everybody for attending. I know everybody's busy, and to actually get something in the calendar where we can all talk about something new is great. So my topic today is research and performance testing of Geogrids for pavement design. So I put this screen up if somebody wants to get to, if the questions weren't answered or whatever, you can look me up on LinkedIn. I'm also on ResearchGate for the papers. Some of the things that you'll see today, you'll find those on ResearchGate. And I share my papers. A lot of times I just have papers in my personal library, and if I get a request, I'll share it with you. Perhaps a little background about myself so you understand where I'm coming from. Back in 1987, that's a long time. I don't know, for me, it was a great time because Dr. Robert Kerner came to me and said, hey, I got this potential book that I'm going to publish. I need you to look it over. And you only had this weekend to look it over. And then when you look it over, you tell me if you want to study this new field called geosynthetics. So when I read the book that had, editors, red lines, and all the other things through it, I looked at it and said, this is amazing. This professor is really looking at a field that nobody's really thought of. And so that's when things kind of took off for me. So I received my master's and my Ph.D. at Drexel University, studying under Dr. Kerner, and learning all about geosynthetic engineering, as well as geotechnical engineering, because the two kind of go together, right? Because with these geosynthetics, we're forming composite structures that we have to design for. So that's a little background to let you know where I'm coming from and the manner in which I present this. So today's agenda, there's a couple of key items that I want to cover. And a lot of people, don't have a full concept of, what type of research has to go behind the materials that we stick into the ground, right? The funny thing is Dr. Kerner actually had a slide, and I don't show it because you can look it up yourself on images, but there's plenty of images showing somebody's head in the sand, right? But he didn't show it because people were putting their head in the sand. He was showing it to say, hey, it would be great if we had the ability to have eyeballs under the ground to see that as engineers, we could refine our design approach. We have a better understanding. We can ultimately provide a solution we know is going to be, is going to last. So in following along in that, in those footsteps, we're going to look at fundamental research that at least our company, TENSAR, has been doing for many, many years. We're going to look at performance testing. And what do I mean by that? I mean, you can do the fundamental research to kind of put your head into the position of seeing what's going on, but then you actually have to then take that information and do performance testing. And then we're going to talk about how we take that and roll that into pavement design. Because of the time limitations, we'll talk about one aspect of pavement design, okay? So, fundamental research. Okay, so the one thing that Dr. Kerner also impressed upon the world by his book that he published, Designing with Geosynthetics, is that we fundamentally design based on the function, right? So I like to tell people, they're like, well, what does that mean to your common person that doesn't know anything about geosynthetics? So what I tell them is, you can buy Velcro, right? And you can buy Velcro to hold your pants together. You can buy Velcro to hold your shoes together. If you buy it, and you can buy Velcro to stick a painting on the wall, okay? So if you put it on your pants and your pants have to go through a washing machine and be agitated, there's different criteria for, how much Velcro is there. If you're putting it on a wall, you better, make sure that it has the proper capacity to hold it on the wall, right? So geosynthetics are no different. You have to look at the function, what we're doing with the geosynthetic, right? Are we putting it in the ground and ask it to separate things and provide filtration and drainage and all these different functions? What are we doing with this? So we're going to cover this a little bit about what geogrids are used for primarily in the field of transportation engineering. We're going to identify the stabilization mechanics and then talk about some of this research that's going on at universities and actually at our facility as well. So stabilization is literally defined as the improvement of the mechanical behavior of unbound granular material by including one or more geosynthetic layers, such that the deformation under applied loads is reduced by minimizing movements of the unbound granular material. So you can see in this graphic, you have the geogrid on the right side, and you can see when it's unstabilized, right? So the geogrid's going to provide the function of separation, and the geogrid's going to provide the function of stabilization. And that's what this graphic shows you. Now, geogrids, many people know, you hear it all the time. Hey, I have this geogrid, but it's got a square aperture. Is this good? Can I use this? But wait a minute, I also see there's one with a triangle. Is this good? Can I use this? And the last, you're going to see one that has 3 different unique aperture shapes. And you would say, well, what differentiates these materials? Well, the key is that as we evolved with our education, in the sense that we did some of this fundamental research, we realized that the shape of that aperture and the shape of the ribs control the behavior of the surrounding material, right? So that's pretty important. So over time, what the aim has always been is to perform fundamental research to find out how these shapes, in fact, before we put these shapes into the market, they're tested along the lines we're going to talk about. But the idea is to increase particle and geogrid interlock, increase that confinement, and increase trafficking performance and value, obviously. So having gone from a square or a rectangle to a triangle, the reason for that first jump was because we realized that particles pack better in triangles. The next jump, which we weren't able to make when we started out performing manufacturing on triax geogrids, was how do we get multiple shapes, multiple apertures into one geogrid? And the reason for that is we also know, although it's great that particle packing is great, that packing is good for one set of particle size, right? So if I have a triangle, it's a single shape. If I have multiple aperture shapes, it's going to get a range, it's going to interlock a range of particles into the structure. And that's exactly where we've moved. And how did we get there? We got there by doing global research. And Ethan is very familiar with the work we're doing at University of Saskatchewan. But we, as you can see from this graphic, we do research all over the world. And this is kind of broken out to understand that the research kind of looks at the end use application, because within that application, the material is doing a number of functions, right? So the primary function is stabilization. So in this case, temporary working platforms, unpaved roads, paved roads, rail systems, and the fundamental research that backs up all this. In other words, before we head out with a new product, we make sure that we're fully testing the product. So back to stabilization. The key here is that by having these particles interlock with the aperture, we also want to make sure the rib is not laying flat. That was the original generation. And the original generation, the biaxial geogrids, were used for embankments and those sorts of things, basically going out on swamps and placing material on swamps. And in that particular case, you were getting separation. And if you needed a geotextile to go underneath it, you would add that. But you would get separation, and then you would get the stabilization, but you weren't necessarily getting the particles to fully interact. This graphic here, it has been developed because if anybody here has been out in the field and watched compaction equipment rolling on top of aggregate, what you'll notice is that compaction equipment's going to push down, and as it moves forward, the ground behind it is sort of lifting up. So we don't want a geogrid that's not going to be able to capture that particle. So this graphic kind of gives you an idea that this newer product, the Interax products, are able to capture those particles much better. And you would say, well, why is that important? Because if you can keep all the particles together, prevent them from moving, you also prevent them from rotating in place, right? You prevent rotation, you prevent movement, and as a result, you limit deformation, right? You're going to have less deformation. By doing that, you also increase the shear capacity of that composite. So that increases bearing capacity, which all these projects desperately need. Let's look at a case where we're driving over top of aggregate that's on top of a very soft soil, but there's a geogrid underneath here. And as you can see, this is a piece of mining equipment. Everybody wanted to prove to themselves that the geogrid was going to work for them, so they built a test section. And there you go. That's what would happen if they put this this material onto the soft soil. So that's what you would see. So what you see here is not stabilization, and basically you have punching failure, right? So in the early days when we started to be able to get instrumentation to see what's going on, we worked with Penn State, and they said, hey, how about if we build ourselves a smart rock and we put the proper instruments inside of it that we don't need to have wires. And we were like, if you can manage to do that, we're all on board. So they managed to do it. And our first set of tests with a smart rock were done to look at ballast behavior, right? What happens under the dynamic loading effect of ballast, which seems to be what a lot of people are concerned about, especially because if you get a lot of movement of particles, as I said, you are going to get particle rotation and movement. And that causes breakdown of the particles over time. And in rail sections, they have to go back and fix that, right? They have to pull the track up and replace that material. And then you would say, well, how do we have them prove to us that this thing worked? Well, they did this little video for us and said, well, here you can see rotation. There it is. And then you can see translation, right? So those were the things we really want to look at. And then during testing, they were able to plot this up. The X is at the center of the smart rock in the non-stabilized and stabilized section. We put these underneath that load right there, right under the load. And so you can imagine you'd have more confinement. You would think you'd have more confinement directly under the load. But as you can see, for the case without the geogrid, you were getting combination of rotation and still getting movement of that smart rock within that system. And if we were to plot this up, looking at the smart rock under the rail seat versus the smart rock under the edge of the tie, you could see very clearly that for the stabilized sections, we basically stopped movement, which everybody was really amazed at. It is pretty amazing when you see this. So this in particular is particle rotation. And again, if we can keep those particles from rotating, that's the first step, right? And then the particle translation. So we do see there is some movement, but the interesting part is those particles, because they were, when you have a geogrid, a lot of people have heard the term compaction aid. The reason they're compaction aid is because when they nest inside the geogrid as you're compacting, they really nest to the lowest potential energy that they potentially would have, meaning they're not sitting there. The way somebody asked the question about this, I said, just imagine if you have a brick. Well, and if you stood the brick on end, it has high potential energy. But if you lay the brick flat, it can't move much beyond being flat, right? So the idea here is that with the geogrid, we prevent the particle from rotating. And that's a result of the unique aspects of the geogrid, basically helping during that compaction process. So we can see here that although there's some movement, you can see the red is the edge of the tie, and you would expect at the edge of the tie, you would expect to have some movement. And underneath the rail seat, as you can see, very little movement. And if we then plot simply the vertical displacement versus the permanent deformation, you see this, there's a dramatic difference. And along the lines of rail, we have the University of South Carolina right now doing some full-scale testing with our Interact products to actually look at that. In fact, we're taking it one step further. We're looking at saturation. So the biggest issue is when it's dry, things could be great, but as that track section gets saturated, things change pretty rapidly. So we're looking at that now. So the other thing we do is we need parameters, right, to put in our design. So as I said, we have to do some fundamental testing. On the right side is a triaxial cell. It's a 0.5 meter in diameter by 1 meter high. And you can see that we're taking measurements of how much this bulges along the extent. So we're getting the lateral strain, and we're finding out this influence. If you look at this graphic here, you can imagine that the geogrid, when placed, has greatest influence around the geogrid itself, right? So the neat thing about this is when we plot this up, what we've noticed time and time again is that if we look at the load versus the axial strain, you will see that when we incorporate the geogrid, there's a huge amount of strength that is imparted. So there's greater ductility. If we look at the curves without the geogrid, you can see it drops off. So over a much larger axial strain range, you get this sort of curve, right? And then we can take this information, we've taken that and we put it into Plaxis. So we've actually developed our own TENSAR stabilized soil model that is utilized to run Plaxis models. And here's the work Ethan's very familiar with, looking at plate load testing, right, up at the University of Saskatchewan. Very uniform soils here that we wanted to test, very soft, with the platform on top. These little blocks are for the video and photos, getting an idea of the influence of this load, the vertical load on the surrounding area. And we're using a 1 meter square plate. You'd ask yourself why? Well, why? Because haul road equipment, heavy haul road equipment, you know, that's the area that they're going to apply. Working platforms, cranes, that's the area that gets applied. So we wanted to have actual information that could be input to design. Now, back to what I said, you saw the large triaxial cell. And if we look at the plate pressure versus displacement, look at the curve. You're getting a similar curve, okay? So that's critical. Now, the latest thing is, so we talked about a smart rock, and we talked about full-scale testing to get some of those design parameters. We talked about triaxial cell testing to get design parameters. The question then came up, okay, you keep telling me, Mark, that this rotation, we see it in the ballast, but the ballast are, you know, that's fairly large particles, and that sort of makes sense to us. What happens for other particles that are more along the lines of a road-based material? So interestingly enough, at the University of Grenoble, they perform X-ray computed tomography. And so somebody's like, wow, what's that all about? Okay, so if you go to the airport and you see these, it looks like a big igloo that your bags have to go through. Those igloos are performing X-ray computed tomography in real time, okay? They're actually able to see your bag and rotate your bag and look inside the bag and see elements inside the bag that are there. So X-ray CT is something that we really want to do work with, and they said, hey, this is great. We can put some geogrid in a cell, and we can you know, place the particles, and then we can apply a load and see what happens. So you have sample prep, you do the scanning, and then you do the image analysis. It's a multi-step process. And I show this is just a sand sample But I show this because they have to rotate this, right? So they perform the X-ray. So this, obviously, it's not the igloo that you see at the airport. And the reason being, at the airport, they got to have these devices all the way around the igloo to shoot across, literally X-ray across the specimen, right? Through a variety of angles to draw the picture for themselves. So I'm just showing that as an example. So here you go. On the left side, we put the geogrid in. We put 2 layers in this case. And the right side, we did not. And so you can see that it's a good size because we had to have the right size of the sample so that we could make sure that all the apertures of the geogrid would fit into it. So having this information and then performing the CT analysis, you can see here that we can clearly see every single particle. So this is like, just imagine every one of these particles is a smart rock for us. So first off, we can see the displacement that occurs, and without the geogrid, there's much greater displacement. And then we can also see the rotation of every one of those particles. So this is phenomenal stuff, right? So just looking at the first case, and we're doing more research along these lines, the stabilization effect is 82% reduction in deformation for the sample and 73% reduction in particle rotation in this sample, which is very impressive, right? Given the variability of aggregates in and of themselves, right? So that was that. Now let's talk about bender elements. A lot of people may have read about this. It's out there on the internet, and you would say to your, well, what are bender elements? Well, the other question that came about is in some cases, some of the tests don't show that we have increased the resilient modulus value as much as we would have liked to. But wait a minute, we know that the deformation is reduced. There's like next to no deformation. So what's going on? So what's going on is that some of the test devices, when you run a test on the surface in the field, you are testing that composite value on the surface, right? So sometimes you're not getting that stiffness. You would actually have to decompose the results of the test to look at what's happening from a standpoint of resilient modulus of that aggregate just by itself in relation to the subgrade. And that's been a tricky thing, right? Because many cases we're using the foundational layer as the geogrid over a soft soil, and then we're putting the geogrid, then we're putting aggregate, then we're putting geogrid again to serve as the foundation for the pavement that goes on top. So this happens for soft soils. So the point is you would have to run those field tests on the subgrade, and you'd have to then run them on the aggregate as well. And then you'd probably have to do some computations to see what's going on. Another way to do this without all the, trying to correlate the results would be putting some bender elements in, right? And the bender element, as we show this graphic here, it's a piezoelectric device where this end element is flapping like a fish. If you pull a fish out of water and it's flapping around, that's what this is doing. And basically, it's measuring the small strain shear modulus of the soil. So this one end is on one side and the receiver is on the other side. And the velocity is taken into consideration to give us that small strain shear modulus. So then we can determine close to the geogrid and further away, we can determine what that effect of the geogrid is. So recently, University of Illinois, Dr. Tudelmeyer did some fundamental research on this, and what they looked at is they looked at a variety of different geogrids. So we talked about how does the shape matter, the aperture, the construction of the material, and the ribs, how does that all figure in, right? So they used crushed limestone along the lines of road material. They looked at 5 different geogrids in the test, and what they found is shown here. So as far as the difference measured between geogrids for the bender elements, there was higher small strain shear modulus measured closest to the geogrid, which makes sense. So we'll see this in a graphic here. And as you get further away, it decreases, right? But also keep in mind, this test is being performed under different load states. But then again, it's not, we don't have like asphalt or concrete on top of this weighing it down, right? So this is just a triaxial cell test. So basically, If we looked at a woven material, you imagine the ribs are flat, it's woven, so it doesn't have that stiffness. Looked at 8% lower small strain shear modulus. A biaxial, 10% higher. A welded material, 13. The triax, which has higher ribs, 18, and 44% higher for the multi-aperture. So this proved to us that you have these multiple aperture shapes that interlocks or increases the statistical chances of interlocking more of the particles within the apertures, has a huge effect. And so along the lines I said at the very beginning, it's achieving this geometry and shape is achieving the goal that we want. So now we've done fundamental research to help get design parameters and also convince ourselves that it is important to prevent particle rotation, and it is important to make sure that the geogrid has the right apertures and the right rib height. So what about larger scale or full scale performance? There's a lot of acronyms that get thrown around. So I put this here. So you got accelerated pavement testing, APT. You got accelerated plate load testing, APLT. And then you have long-term performance. So long-term performance is actually going out in the field and, for example, using technology to get the International Roughness Index, right? Because if you have a stable structure, that IRI should maintain itself over time. But we're going to talk about some of these things here. There are research reports readily available for the things that I'm showing you today. And so if we look at the accelerated pavement testing, the idea there is to basically prepare a road section, in this case, an asphalt paved road section, and have a section without the geogrids and sections with the geogrids, right? And I'm going to show another video, hopefully that will work for us. But you can see there's these elements for heating the chamber, and then doors go on the outside of this. And the wheel's not here yet, but there will be a wheel. For this most recent research we did, we looked at interacts in comparison to the control, and we also changed the thickness of the layers so we have an idea on the design parameters and how well those design parameters can be utilized in the actual design. And you have to instrument the heck out of it, right? So a lot of instruments replaced, multi-depth deflectometers, subgrade earth pressure cells, base course pressure cells, and asphalt strain gauges, right? So throughout this. So the idea for the multi-depth deflectometers is to look at each of these layers and see how they're moving as the wheel is moving along the surface. Oh, so the audio came on regardless. So here it is. Here's the wheel loading. What you'll see here is that this darker color in the center is because we don't do channelized traffic. You actually want to do traffic that would be realistic in the field. You have wander on the road. So that's what's going on. And you can see here that we have basically an environmental chamber, because we have these panels, you can see them over here, are placed on the outside and they're insulated so that they can maintain the temperature. So we want to maintain proper temperature inside and traffic the pavement section. Now, automated plate load testing, that is, that you imagine that we've got all these design parameters, we've done the testing at the Corps of Engineers, and then somebody says, oh, you know what, that's all great. What about in the field? What are you actually getting in the field? Well, if that's the case, we need to actually do plate load testing in the field. What you see here is the piece of equipment. The equipment has to be weighted properly so that it can resist the force associated with the plate load test. You also have to have these steel bars here, because what are they doing? They're actually measuring the deflection bowl that occurs as a result of this load. Now, every project's different. You would say, well, why don't you just run one or two tests? Well, we had to run a lot of tests because each environment and each aggregate is different, obviously. We try to get this parameter along with the large triaxial cell parameter that you see. So, for example, we can fill in the gaps of our knowledge. So if we have this could be a crushed limestone, we may have another different type of material. We can actually test those materials in a large triaxial cell and see how they fit in with the results of this sort of field work, right? We've also gone ahead and looked at taking all this information from the field, and we can then put that into a neural network and do analysis for deformation. So here's a graphic just showing you that there are dramatic differences in deformation that occur with and without the geosynthetic. So the bottom line is permanent deformation, right? That's what the end user wants to look at. What's going to be the effect of having this geogrid? And in many cases, people would like to save money on the road, so we're making the roads thinner. And we want to make sure that the permanent deformation is minimized. That's the goal. So that's easily done. The other thing that's important is that we want to make sure tests are done over a lot of climatic zones. And that's important for mechanistic empirical. I don't have time to go into that today, but that's very important. So not only have we done a lot of testing in the West, we refer to this as the Western Hemisphere, we've done testing in the Eastern Hemisphere as well. And we've been doing this plate load testing since 2014. Our database is massive and gives us really the information we need to assure our end users that our design is highly accurate and is going to yield the results we say it's going to yield. So APLT tests were initially used for field verification when we were in the research phase, but then it rapidly moved to our field engineers just using it to collect data and also assure the customer that, hey, we designed it, here's our design, and this is the result you're getting from the actual tests in the field. And we were the first, TENSAR was the first in the industry to do this sort of work. So that's important. And as I said, getting to the fact of using machine learning techniques, we're doing that as well. So now that we have this massive database, think of what we have. We have the tests done at University of Saskatchewan, for example. We have tests not mentioned. We have the large triaxial cell, we have accelerated pavement testing, we have APLT in all these different temperature environments. The next step is to take all that and let AI take over, right? Let's model this. So we can actually model permanent deformation and be highly accurate. Okay, what about long-term pavement performance? Some people say, oh, well, I'd like to, how do I check to see that this new road that we just designed and built is going to work? Well, we know it's going to work. And we've been doing long-term pavement performance as well for a number of years. You can download an app on the phone these days. And then from that, we establish, basically you're getting that vertical movement over distance on top of a road to compute the International Roughness Index. We use a company called TotalPave. There are a lot of companies out there today. But basically, you're using all the technology built into your cell phone, which is placed on the windshield of your car. And, it was interesting because we had some engineers saying, well, wait a minute, paid all this money for a profiler. You're telling me this is going to give similar results? And guess what? It does. It's been proved, and there's papers written on it. You can look them up from the TRB conferences and from the websites of folks like TotalPave. And we keep all that data, right? So we have a large database of all this information. And from this information, two things can happen. Before somebody wants to do road construction, they themselves run their profile across those roads, right? And they determine what sections are really bad and what are not. The really bad sections need geogrid designed into them, right? Because there's likely some foundation conditions that demand it. This is a case where we had a project out in Arizona, and this is over a period of, I think it was this is in 2019. So this is a snapshot, but 4 years, so roughly 4 years, and looking at that performance over that time. And it's pretty impressive. We're doing this all over the world, and we've written a lot of papers about this. And most recently, for the Interacts, we went to a quarry and asked them to use the quarry to look at several different scenarios and evaluate that permanent deformation at the quarry by looking at the Interacts geogrid. when we looked at this table, it's hard for you to, given the time of the presentation, but in general, we were looking at traffic that was nearly 30,000 passes, 100 kilonewton loads, 100 kilonewton loads. So if we look at the profiler scans, what we found is the sections with the geogrids outperformed the counterparts. Basically, we had different sections. So we had, in the first couple sections, 1 and 2, we were using a good aggregate. In the second sections, we were using RAP. So you can imagine RAP is going to, in and of itself, is going to deform more than a good aggregate. So as far as with the aggregate itself, 38% reduction in deformation, and with the RAP, 13% reduction. So pretty significant for them based on the quarry, based on the loading, full trucks. Now we take all that information and we can put it into a design approach. The one that I'm going to talk to today is the AASHTO 1993 method. Many of you are aware of that. We have design software that runs through these calculations and is predicated again on the research that we've done and R5009. So it's R50 is the document. It's the geosynthetic reinforcement of aggregate base course of flexible pavement structures. So if we look at the fundamental design equation that we're dealing with, what does the geogrid affect? The geogrid affects the structural number, okay? So what is the simplistic equation? So the structural number drives the thickness required for the pavement based on the loading. And it's a simple equation. It's really a structural coefficient times the thickness of each particular layer. So the first one is your asphalt, your aggregate, etc. If you have multiple layers, you can carry that on. So again, this is the asphalt, this is the aggregate base, and this could be the sub base and other materials, right? Depending on what you're putting in the road cross section. So if we look at unstabilized, you can see here that you would have A1D1 and A2D2, and the stabilized, the same with the geogrid. So what are we changing? So there's your equation. There's a base equation for this. There's going to be a factor that gets applied to that structural value when you incorporate the geogrid. So that's where it gets applied. And that's how it affects the structural number. So I just put this over here. That's the layer coefficient ratio. Again, that's in that document R5009 if you want to read more about it. Right there. And I just put this in here as an example for the report. Now we can go to TENSAR Plus. And the nice thing about TENSAR Plus is you can put the design in place. You have your HMA layer thickness, you can have multiple layers, and you have the aggregate base. You can place that in there, select the geogrid. You put in a subgrade resilient modulus, whether you want a separation geosynthetic, put your reliability, standard deviation, serviceability, initial and terminal to drive the calculations. And then we can also perform right in here the cost calculations. And that's how you get the value out of all the information that I just presented. Furthermore, what we also realized is that incorporating the geogrid is going to affect the construction cost, right? So the idea by incorporating geogrid, sometimes we're extending the life, which means we would keep the sections the same thickness. But most times people want to reduce thickness if they can get the design easels that they were looking for, because everybody's budgets are tight and they want to design for a certain amount of time, and they want to make sure that this is saving them money in the end. So you can see here, we can compute that construction cost. The other thing is construction time. And a recent case that I bring up for people is the Illinois Tollway Authority. What they did was kind of unique. People were pushing back at the time, this was a couple years ago, pushing back on using geogrids at all. And the engineers said, well, no, we need to use the geogrids, because if this road does not open by October 1st, there's penalties, right? And to help make sure that does open October 1st, we're going to put a geogrid section in there. And when we put the geogrid section in there, if you can't achieve your goal, you have the choice to move to that geogrid section. So on that particular Illinois tollway projects, there were three contractors involved. Two of the contractors used the original section to start the project. The contractor that used the geogrid finished the project well ahead of schedule. And I think the others looked at that and said, we're running up against time constraint. And then they switched over to using the geogrid. So I guess the point is, even for people that are hesitant at first, it's always good to incorporate a geosynthetically designed section into designs and allow for that flexibility, right? But that case, they were not really looking at or worried about that cost. They were worried about achieving the easels on the road. Okay, but if you're someone, an owner or company that's interested in maintaining your costs, you wouldn't head that route. You would just say you have to use the geogrid section period. So the other neat thing is within TENSAR Plus, and by the way, this is all free, right? And so a lot of people on this call, you may be studying about this information. So if you're studying this or you want to learn more, the beautiful thing is that we include resources into the software that help, right? And what I mean by that is you can go into the resource section and you can select the resource section. Then you can go in and pick a particular topic. And then once you pick the topic, you have access to both white papers and research papers that some of the stuff I talked about today, or it's related to what I talked about today, right down to numerical simulation, for example. So all this information is there. It's readily available. And I encourage you to visit TENSAR Plus, if not for anything, to find out what tools are available and what resources or research information is available for your use. So what have we learned today? Let's see what we've learned. So the fundamental research tells us that geogrids prevent particle rotation and translation. So this leads to maximum particle-to-particle interlock and increased shear strength. And again, some geogrids do this much better than others. And the reason I say that is because when somebody is giving you a design solution, that design solution will be related to the type of geogrid. So for example, for TENSAR to give you a triax geogrid in a pavement, I would give you a different cross section in comparison to one section I would give you using Interax. You have to make that choice as to whether you want to go with that thicker section or the more economical section, right? So you need to look at the solution, not necessarily, everybody will say, well, my geogrid works. Well, nobody's claiming that any in particular geogrid does not work. That's on what my presentation is all about. My presentation is about the fact that as I make that cross section more economical, as I make it smaller, I want to assure myself that I'm preventing particles from getting broken or crushed because I'm minimizing rotation. I'm making sure that the particles are confined and they're not going to move. And so when you get all that, that's critical. Another case in point, if anybody's ever stood out on a concrete, the easiest way is to do this is concrete highway. And usually you can only do this during construction. And we were actually at the Illinois tollway before they were actually going to do the construction. We were on the old sections. And we were standing out in the old sections and we were doing accelerated plate load testing because the idea there, which was pretty smart by the engineers, was, hey, let's go out to the old sections, cut a hole through the concrete, and go down to the subgrade and do APLT on the subgrade. So we have a better idea of what the subgrade strength is, so we can design this section properly. At the same time, we could also test some of the aggregate on that's still there underneath the concrete, see what's going on there. But the thing to me that was very interesting is, I raised this to others, do you feel the movement in your feet from the cars passing by? And they're like, yes, that always happens. I said, but you realize that means that this is vibrating. The structure is vibrating. If the structure is vibrating, those particles underneath are moving, right? So that's why these particles break down over time, and I don't think people give that enough consideration. Only people physically going in the field can get a real good feeling of that from their senses from your feet on the ground, so to speak. We learned today that full-scale accelerated pavement testing is required, right? Full-scale triaxial testing, APLT with site-specific aggregate is ideal. Pavement cannot be designed without this validation and calibration, and you now have really everything you would need to do a proper design by going to TENSAR Plus or run your own hand calculations if you want. So with that, I'd say thank you. I'll leave this up and we'll answer some questions. And I appreciate everybody attending today. So Ethan, you can take there you go.
There you go, I'm back. That was great, Mark. Thanks. For the presentation. We do have a couple questions queued up, and then, yeah, if anyone else has questions, we'll probably take about 15 minutes for questions. So throw them in the chat if you guys have any more questions. First question that I have for you is how do Geogrids work under RAP, and what are the specs for using RAP?
Okay, so each state has their own specifications for RAP. So if you go to Colorado DOT, they have a specification. In other words, what they require as far as getting it to the proper sizing. So you can look at that. You can have AI do a search. If you're just trying to get a general understanding, you'll find Colorado has done some phenomenal stuff on kind of determining what you need from a specification standpoint. And as you saw, we did full-scale testing, actual live testing with RAP. And again, depending on the size of the RAP, that drives kind of the behavior. And depending on where you're going to use the RAP in the field, are you going to use it under concrete pavements, under asphalt pavements? Where is it being used, right? So in that sense, we've run the test to kind of understand. We've run tests on crushed concrete, RAP, and other materials, so we kind of understand what it would do. But I can assure you that you would want to look state by state, because it depends on what asphalt materials are using in the highways, right? Because there's so many different blends and mixes of these. I would look to the municipality or the state for what their guidance is on the RAP itself. And then if we need to test, we can run our testing, in triaxial cell to get the better, even more refined design parameters. We have an idea from our past work where we did APLT, accelerated plate node testing, but we had a case in Colorado. We put in the interstate that runs through downtown, and we did K-value tests, plate load tests, large diameter plate load tests, right? And to assure them that those parameters are right for the asphalt pavement, for the concrete pavement. So that's what we did there. Hopefully that answers the question, but like I said, you have to do a little more research for your particular needs.
Thanks, Mark. Got another one. What do you think is the prospect for research in geosynthetics in the era of AI? This person also says that they're considering going for a PhD in the topic, and they're worried about outpaced or being replaced by AI.
Well, I manage a group of engineers myself, and it's funny because some people, I actually had one lead engineer say, I was kind of waiting for this to all blow over. But we know that's not going to happen. AI is not going to blow over. And there are some people that made a presentation to this person. And the presentation, the line that I liked most is the person presenting said, you're not going to be replaced because of AI. You're actually going to be replaced if you fail to fully utilize AI, right? And in our area, I think having a license in engineering, there's no way we're not going to have robots or AI take over the responsibility, right? Because there's liability for what we do as engineers. And so, for example, I think there's even a greater need for people to get their PhD in areas like this and research. And why do I say that? Because what other engineers are going to want to draw and say, wait a minute, yeah, AI had run an analysis. It's great. It can run analysis of all that, but it can't take people are saying it will give engineering judgment. Now, what it's going to give you, like I say, Microsoft did it right. They call their use of GPT-5 and 4.0, what they call it is Copilot, right? So I view AI as the Copilot, and as licensed professional engineers or engineers that have PhDs or master's degrees, we are the pilot. So what do people want us for? They want the pilot, and they always will want the pilot, because if somebody has to go to somebody and said, this happened, what went wrong, they want a human there. They don't want a robot sitting in a stand. They want a human sitting in the stand saying, hey, you may have used AI, but how did you just accepted everything AI said? And you better say no, because you're basically, like, even when I run AI and calculations, I tell it to show me your work. I want to see your work, and it will show it. So AI is just another tool. It's an advanced tool, and it helps us study. It helps us learn, but it cannot possibly replace the experience. Our lived experience is going to be essential. So no, I've encouraged my engineers to not only get their advanced degrees, but I've said to them, you should be licensed. If you're worried, if that, everybody has a different feel for this, but I would say if you're truly, honestly worried about that, become licensed. Because guess what? Bottom line, you could be used in litigation cases, because there's going to be more litigation cases in engineering in the next, within 5 years, when everybody starts using AI, you watch the explosion of litigation cases from people that just threw it out there, just used AI to build something, and a freaking bridge fails. You see what happens if that happens. But I'm just saying, if that happens, there's going to be more litigation. There's always going to be room for everybody attending this session. There's always definitely going to be a place in the world. In fact, I would say you're going to be more highly valued. And so the reason I point to one area, and here's the one area. So I listened to all the podcasts and everything. And so one interesting thing is, in the very beginning, they thought radiologists would not be needed anymore. But guess what? They still need that radiologist to testify. If AI said, pointed to this and said this was the problem with the patient, and that AI was incorrect, you can't sue AI. You can't take AI to court. So guess what? Radiologists have streamlined their functionality, right? They streamline their functionality. They actually can take on more patients, and because they can take on more patients and more workload, that their salary is going up, right? So in the U.S., I don't know about Canada, but in the U.S., radiologists make almost $600,000 U.S. a year. Okay, if you want to become a radiologist, go for it. Because what I'm saying is, that's the pilot. The radiologist will always be the pilot. They're going to be responsible for the decisions that AI is making. So hopefully my soapbox works for everybody. But that's my personal opinion.
Right. I got some more questions now. Oh, that's a long one. All right. I want to understand what would be the percent increase in the modulus of elasticity of a soil geogrid system, such as a geogrid between a base and a subbase. Is there any particular research done to support this? What type of TENSAR geogrid is suitable for this? As well, they say, what is best tool to do the numerical analysis for this? LEA from Plaxis, Abacus type FEM tool.
Yeah, so in this short time period, what I would say to you on that is that our research showed, the reason we went ahead, so we now have that 0.5 meter diameter by meter high triaxial cell, both in the UK in our production facility, and we have it here in south of the airport in Atlanta, Georgia. And why did we do that? Because you can't put a number on that value. Everything is specific, right? So we, as a company, made the decision to invest the dollars into actually doing the testing to get the actual values. I think I explained to you before that there's still an art and not a science to computing that increase in resilient modulus, for example. We know from what I showed in the Bender elements that small strain shear value is phenomenally high when we incorporate the geogrid, which means that's why we're seeing no deformation or very little deformation in these composites, right? So the point being, until there's definitive science, we're doing the testing that needs to be done to assure our end users that the software is generating the answers that it should to give the design cross-section. So hopefully that answers that. Now, as far as the other part was the modeling. Again, we have a TSSM model that can be plugged into Plaxis, but that model is used for foundations and that sort of thing. We're working on another model because, as you can imagine, when you look at repetitive loads, that's a whole different calculation case. If you're interested in getting a hold of the TSSM, you can send me an email. We can link up on LinkedIn. In LinkedIn, I can get your email information, and we can send you the agreement, and you can get that model to plug in to Plaxis to take a look at that, if that helps.
All right, next one we got says, looking ahead 3 to 5 years, what are the top few R&D priorities that you see for continuing to improve pavement foundation performance, and what additional steps are needed toward greater implementation of AI?
I think a lot of people on this call would understand the concept of computer vision. I think, we're moving so quickly now with AI. My idea is the fact what we're doing. So as we do large triaxial cell tests, we are quantifying the behavior of the individual particles at the same time. In the next 5 years, we'll be heading toward the fact that we can go in the field and take video clips of that aggregate, convert those video clips, actually frames of those clips using computer vision and maybe some newer technique, maybe even computed tomography. If we can get it to that point, have our own igloo. Because the point is, you really need to, I think most people fail to understand when most people may or may not hear of superpave asphalt materials. Before they came up with superpave, they said to themselves, well, the thing that drives asphalt, and by the way, it's no different for aggregate. What drives asphalt is the angularity, the particle shape, and the F to E ratio of those particles. And you can go out and do your research with AI. It'll give you a whole list of all the papers. We do that as well, right, for what we're doing. So you can imagine in the future, the research should head toward how do we actually we can go to a quarry that's going to be used, or we can look at RAP or crushed concrete or whatever the material is, and really draw an inference of whether that material can be used to build a road or something with it. I think that's where, because AI is moving so quick, AI can help us crunch through all that information where it wasn't even physically possible before. So we're already using AI to analyze our data as we go along. And again, I expect that ability that I should be able to just go to a quarry and use some technique at the quarry and say, the stuff over here is good, stuff over here shouldn't be used. And if it is used, it has to be used in a thicker cross section versus this stuff over here. I actually think that's where it's heading. So yeah, there's a lot of research that needs to be done to get to that point. I know there's a gentleman from UIUC. I think he went to work for Meta or somebody else to use computer vision, but they were using it for rail systems, right? So cutting through, when they have a problem at a rail section, they need to actually replace it, but they also now go with cameras and they do computer vision to check on the fouling index of that material to kind of see what state it is in. And they're working on these same sort of techniques in rail. They want to be able to have a more accurate level of knowledge on each kilometer of rail as to what would need to be fixed and when, right? You have to build, so think of that. So there's a whole workflow here. So you can look at all your roads, build an inventory of those roads, because everything's an asset. So we talk about asset management. So AI can be used in asset management to see what needs to be done and move from there. So there's just so much great information that we can gather and research that can be done, whether it's an X-ray CT, whether it's using smart rocks. Now they have smart pebbles, but there's plenty of research to go around because, again, AI is a tool to help us get the answers, right? So there's plenty of research that can be done.
All right, we'll do one more question. and then probably call it after that. So the last one I got for you is, in your experience, at what project scale or traffic loading does Triax typically reach a break-even point when considering the upfront cost versus savings in aggregate reduction, construction efficiency, and long-term maintenance? Additionally, is the system still economically feasible for smaller scale residential or commercial developments, or is it more optimized for high traffic or industrial applications?
Oh, that's a good point. Again, the numbers, I don't like throwing numbers on stuff unless I run that analysis because they vary widely, right? So you should go to Tensar Plus experiment as far as numbers, but I would say the interesting thing as far as residential and all these other areas, what people have failed to understand, and I actually picked this up at an ASCE conference. There was an asset manager talking to a pavement engineer, and they said, we have a massive challenge when it comes to residential, lower volume roads than we ever had before. And the pavement engineers, what? Tell me more. Well, think about this. As all these vehicles get automated, what's going to happen? I showed you our accelerated pavement testing. We wander, right? So if they don't wander this equipment on the road, you're going to have channelized traffic, which destroys a road. Not only that, it doesn't matter where that road is. In front of my house, where I'm at right now, you know how many Amazon trucks I get coming through here? I get Amazon trucks. I get all that loading. This road was never designed for that level of loading. So there's going to be a big challenge because then if it's automated, maybe guys haven't read this, but so Amazon is going to mandate Q1. They should have their virtual reality Amelia glasses. They're going to require their drivers to wear, and it'll help give them helpful hints on directions, package, all this other stuff. But that's not the point of them wearing the Amelia glasses. And there may be a battle come 2026. The real reason for wearing it is that all that data is going to be put back into robotics. They literally want to have a robot drive that vehicle to your house and put the package on your doorstep. No human involved. It can work 24/7. There's no holidays. The weather doesn't matter. So I guess that's kind of my thought right now. I don't know what more I can say other than, like I said, the Geogrid can be used in these applications, whether it's a road in front of your house or a low volume road, to not only extend the life, but the big thing is IRI, right? Because that minimized permanent deformation plays a critical role in how this whole system works, right? How our roads work. So, and so another thing to look for yourself, which is interesting, if you go to a big box store, what you'll notice is a lot of times they'll have concrete pavement out back, right? They have asphalt in the front. Well, why do they do that? They're trying to be economical as well. The concrete's because all the 18-wheeler delivery trucks are coming to the back. All the cars are driving to the front. So if we look at an easel, if people are familiar with an easel, you're looking at 5,000 easels for a car, for example, is a fraction of what a truck will be, right? So that's important. Does that make sense? Hopefully that makes sense.
I think it makes sense.
I guess what I'm saying, if you have a car and you drive it, you would have to drive over the area 5,000 times, right, to equal one easel. And so an easel is roughly, an 18-wheeler, if that makes sense. So every time that 18-wheeler is running through the back of a box store, that's why they put concrete. They put a thick concrete section back there. They kind of do overkill, right? So they spend more money on that. And then they put a thin asphalt section in the front. My point is that with these new, the way we're delivering things and moving things around, we're going to have automated. The cars will be automated too, by the way. So they're going to be driving and putting channelized traffic. So I suspect whether it's in a subdivision or anywhere else, you're going to have more damage to the road. I guess that's the bottom line. That's it.
Okay, I think so. Yeah. Thanks, Mark, for your time and your presentation. That was excellent. And thank you, everyone, for attending our webinar series. Our webinar series is every second Wednesday of every month. So if you guys tune into our LinkedIn account, take a look and watch out for the next one. If you guys have any more questions, Marcus said feel free to connect with him over LinkedIn. So reach out to him. He's a great resource. I like talking to him about geosynthetics and when he comes out. So it's always a good time and very knowledgeable guy. Yeah. So thank you, everyone. Oh, and if anyone is interested, for the CGSYP, we are having our annual general meeting as well tonight. So if you guys are interested in participating and joining, please check out the LinkedIn and you can register to join for that.
Thanks for having me.
Thank you.
Okay, take care.